let's say I have a bucket of aqueous solution and it contains some weak acid in it. And so weak acid, we've done this multiple times. It's in equilibrium with its dissociated state. So it would be in equilibrium. Let me write the aqueous. So it's a weak acid where the A could be any other kind of molecular group. That could be the conjugate base of the weak acid. So that's in equilibrium. That's in equilibrium with some hydrogen ions. So it'll produce some of them, but some of this is going to be around as well, plus its conjugate base, A minus, aqueous. And just like we did with the strong acid titration, let's measure its pH. So I'll do that right here. And let's say our first, actually I want to do a little higher. So let's do it right there. So let's say our first pH, so let's say, let me make a little scale here. So this is 0. Let's say that this is, that right there is 7. That this right here is 14. So our first measurement of the pH of our solution, we have maybe a liter of it. Let's say we have 1 liter of our solution. We don't know the concentration of this thing. But let's say our first measurement, we go and we say, okay, it's got a pH of, I don't know, something here. Let's say it's got a pH of 3. So it's acidic, not ultra acidic, but it's acidic. So it's got a pH of 3 right there. This whole scale on the left-hand side, this is all pH, just like in the last video. This is pH, and pH is going up as you go up the scale. That's our first measurement. Now we're going to titrate this weak acid just like we titrated the strong base. And normally when you do this, I mean, you can, in theory, titrate with anything, but you normally titrate, if you're titrating an acid, whether it's weak or strong, you always titrate with a strong base. And if you are titrating a base, whether it's weak or strong, the reagent or the thing that you're going to add is going to be a strong acid. So in this case, even though we're going to drop some drops into a weak acid, we're going to drop drops of a strong base. So we're going to use, let's use sodium hydroxide again. So NaOH. And just to make things interesting, to make the math a little interesting, let's say it's a 0.5 molar solution. And we're going to add it in increments of, we could add it in little 100 milliliter increments, 1/10 of a liter. But the interesting thing is really the shape of the curve that forms, or the titration curve, or the pH curve. So what's going to happen as let me write the reaction of NaOH, just so you have that in your head. NaOH, sodium hydroxide, and I did this in the previous video, it dissociates completely in water. And so it turns into Na plus, all of this is aqueous, of course, plus OH minus. So when you throw even a little bit, let's say you throw in, this is 0.5 molar solution. So let's say you throw in 100 milliliters. 100 milliliters. That's equal to 1/10 of a liter. This 0.5 molar, that's its molarity. So it says, hey, I'm going to have half a mole of this stuff, or really of this stuff. I'm going to have half a mole of hydroxide ions for every liter. So in 1/10 of a liter, that means that I'm going to have what? I'm going to have half of that. So I'm going to have 1/20th, or 0.05 moles. So let's say this point right here is 100 milliliters. I've added 100 milliliters of our solution. That's going to have 0.5 moles of OH. Because remember, we could say it's 0.5 moles of this, but whenever this is in solution, it dissociates completely into this. So if you have 0.5 moles of this, you really have 0.5 moles of this. This will be in this form completely, because it's a strong base. So if I have 0.5 moles of this, and I throw it into this solution, what's it going to do? It's going to start sopping up some of our hydrogen ions. So it's going to increase the pH. So the pH is going to increase. pH is going to increase, and it's going to keep increasing. Right? It's going to keep increasing. And remember, this is a buffer. And just this is a key thing to remember. This is going to sop some of this thing up. But this is a buffer. This is a weak acid. So it's in equilibrium. So it has this reserve over here of the acid form. So when you start lowering this by adding a strong base to it to sop this up, what's going to happen? The reaction is going to move in this direction to kind of backfill, to fill, or to almost replace. It won't get quite to where it was before, but it's going to dampen the stress on the equilibrium. So what's going to happen is the concentration of your weak acid is going to go down, because it's going to try to backfill this stuff. But every time the reaction goes in this direction, this is going to go up, right? Remember, nothing is stopping up the conjugate base up here, right? We're just sopping up the hydrogen ions. As we sop up more and more hydrogen ions, this reaction goes more and more in the rightward direction. But as it goes more and more in the rightward direction, we're just adding more and more to this. And we just keep taking, and the base just takes more and more of this out. So essentially, when the base is taking this out, it's really taking this out, or it's taking half of this out. It's taking the H part of this out, because that converts to that, and it gets sopped up by the reagent, the strong base, and all of this ends up on this side as the conjugate base. So at some point, when we have added the exact same amount of OH as there is of this stuff, as there is of this stuff plus the hydrogen, when we've sopped up all of the hydrogen, what's going to happen? Well, at that point, right when you get above that point, when you start adding even more, you're going to start getting very basic. You're going to start, it's just going to skyrocket up the pH, because then you're adding OHs, and they're not being canceled out by any hydrogen out over there, and there's nothing to kind of backfill the hydrogen. So you're going to get to a very high reaction. But what happens when this this neutralizes? So when the OH, when we add enough of the sodium hydroxide that this is completely neutralizes this, and all we have left is that. Well, you might say, oh, well, maybe we have a pH of 7 because, all of the acid is neutralized. But we don't have a pH of 7 like we did with the strong base, because here, as we sopped up stuff, we kept adding conjugate base over here. Remember, and it's a real base. It actually has basic properties. If this was a strong acid, you might say, oh, I have, if this was hydrogen chloride, I still had the chloride over here. But chloride, even though it's the conjugate base, it has no basic properties. It does not increase the pH of a solution. But this stuff right here does increase the pH of a solution. And we've done that in previous videos. So once all of this is sopped up, your equivalence point, or the point at which the number of moles of this is equal to the number of moles of this, is going to have a high pH. So it's going to be like right over there. And then as you add more and more of your reagent or your strong base, your pH is going to get higher and higher and approach 14 or even go above it. So your titration curve is going to look something like this. It's going to look something like this. And once again, you look at the steepest point on the curve. It's right there. And you say, OK, that's the equivalence point. That's the point at which I had an equal amount of hydroxide having sopped up all of the hydrogen, and I've run out of all of this stuff to backfill the hydrogen. So you look at your equivalence point, and you say, OK, if that equivalence point was when I added, I don't know, maybe that's when you added 2 liters of your reagent. So you added 2 liters of your reagent, your basic reagent right here, or your titrant, I think, or titrator, I think that's another word for it. How many moles have you added? Well, it's 2 liters, it's 0.5 molar, so you've added 1 mole. So here you've added 1 mole of OH, which implies that, and when you added 1 mole of OH, you sopped up all of the whatever mole you had of this. So you clearly had 1 mole of that. So over here, your original concentration of your, I mean, you really could say your concentration of your HA plus your initial equilibrium hydrogen is equal to 1 molar. Now, in most chemistry classes, this number is way bigger than this number for most weak acids. And you can look at that, because if you look at some of the pKa's for some weak acids, you'll see that this is some, this is, well, I won't go into the math, but this number is a lot lower. So this is an indication, essentially, of your initial concentration of your weak acid. So you essentially just keep titrating it, figure out the inflection point. You say, hey, the inflection point happened when I added 2 liters of the titrator to it, which corresponded to 1 mole. So therefore, I must have had 1 mole of my original acid in the equation. Now, Another interesting thing. So if you said, okay, I had 1 mole of my original acid in the equation. So you say this was 1 molar originally before I started titrating it all. And if I say that this is a 1 liter solution, then I know what this is 1 mole, not 1 molar. But if I know it's a 1 liter solution, now I know that originally I had 1 mole in 1 liter, so I had a molarity of 1. Now, let me go over something else that's interesting about a basic reaction. Actually, let me do that in the next video because I think this one's getting a little long.